Hello again. This is the last video for review for test 3, and here I will talk about chapter 11. So we discussed correlation and linear regression, and I will use this example right here to go through the main ideas of this chapter. So what are we trying to establish here? The main goal of this problem is to figure it out if there is a linear relation between the two variables. Okay, so you will be given a table with ordered paired data. Okay, so x and y, and x we call explanatory variable, and y is the response variable, or the one that you will be predicting based on x. And our main goal is to figure it out, is there a linear relationship here? Can we come up with a linear model to predict values of y? Okay, so the first thing that you should do is plug in these values into your columns. So let's say in L1 and L2. All right, now a scatter plot is the first thing that we need to take a look at to make a conjecture if there is a linear relationship or not. So let's go ahead and do that. Now all my data is already plugged in my columns. So how would you do it? Go to stat edit, and you see that all my numbers are already here. Now I'm gonna go second y, activate one of my plots. I'm getting scatter plot, L1, L2, everything is good to go. So I do zoom 9. That gives me a scatter plot corresponding to this data. Okay, now let's say I ask you to sketch it. What I'm really looking for is just a rough sketch of what your scatter plot would look like. So here's x, y, depending on what the problem is. So let's say this is price of product A and this is price of product B. So you would say, okay, this is in dollars, the units are in dollars. Then what would you do? Just roughly put the points over here. So something like this, right? Here's another one here, and then 2 more there, and 1 more up here. So just a rough sketch would do it. Okay, then we'll look at this, and what can we conclude? Well, it looks like this is a very strong positive linear relationship. Okay, so that's our conjecture. So what would I say? The form here is linear. The direction is positive, and the strength is pretty strong. Okay, so strong. Okay, looks like all of these points are clustering around a line with a positive slope. Okay, so that's form, direction, and strength. Okay, now correlation coefficient will actually tell us how strong that is, right? So to compute the correlation coefficient, there's one thing that we need to remember. We need to turn the diagnostics on. So diagnostics on. How do I do this? You go to second catalog, and I need to find D, so it's this letter here. Diagnostics on, enter. Okay, and now when I compute my linear regression line, it will also produce the correlation coefficient. So I'm going to go to stat, linear regression command 4, L1, the independent variable first, L2, independent variable second, enter, and my R is actually really big, right? It's relatively close to 1, so let's call it 0.994. Okay, so R here is 0.994. Okay, so this is confirming our conjecture that we have a fairly strong linear relationship here. Okay, that is very close to 1. So close to 1. Okay, now here's a quick warning for you guys. R alone is not a good indicator if your model is a good model for the particular situation. Sometimes you will have problems where R is fairly large, but the scatter plot doesn't resemble a line, and that's when you need to do hypothesis testing to figure it out if particular data can be modeled with a line. Okay, so we'll get to that in a minute. So here's your R. So far it's confirming that yes, looks like there is a positive linear relation. Now your least squares regression line. How do we compute that? Well, it's actually already done, right? You do this computation here. So let's go ahead and write down our model. Y hat is, let's see, what is it? What is my a 0.1, 1.7, let's call it 7. So 1.77x and let's call it 895. Let's call it 0.9. Okay, so that is the line that we're going to be using in predicting values. Okay, least squares regression line. Let's go ahead and talk about residual values. Let's say I would like to find y hat, or predict the value of y if my x is, let's say, 18. Okay, so if my x is 18, then I would do 18 times 1.77 plus 0.9. Okay, so let's do that computation real quick. So 0.9 plus 1.77 times 18. Okay, 32.76. This is the value that your model predicted for x when x is equal to 18. Okay, so that's the predicted value. What is the residual? The residual is y minus y hat, meaning what? The actual value from the table minus the predicted. Okay, the actual minus predicted. And the most common mistake that I see, students using x values for some reason instead of y. Okay, so what you need to do is the following. You go back to your table and you take a look and find the y value that corresponds to x is equal to 18. It's 31. Okay, so 31 minus 32.76 is equal to what? Negative 1.76. What does it tell us? It tells us that the model overestimated the value of y when x is equal to 18 by 1.76. Is it a lot? Well, I think it's pretty good. Okay, this is your error and it's not that large. Okay, so this value right here is relatively close to this one. Okay, and that's actually what your line is doing when your calculator is searching for this least square regression line. What it's doing is the following. It's finding these distances between the actual values and the predicted one and finding a line that has the smallest error. So it squares all of these distances, adds them all up, and finds the line that has the smallest error overall. And that's why it's called least squares regression line. Okay, so for this particular one, the residual value is this. This is the residual right here. It's the difference between the actual and the predicted. And in this case, for this particular x, for x is equal to 18, the residual is 1.76. That's pretty good. Okay, so that's what the residuals are. Now, interpreting the slope. How do we do this? In the context of the problem. So your slope is the number that's attached to x. So in this case, it's 1.77. What am I asking you to do here? Write a sentence like this. For every 1 unit of X. So if it's price, we say for every $1 in price of product A, Y increases by how much? By 1.77. Okay, that's the interpretation of the slope. For every 1 unit of X increasing, Y is also increasing by 1.77. Let's say you had a slightly different example. What if you had something like this? What if your equation looked like this? Y hat is equal to 2.5 minus 3x. Okay, in this case you would say for every 1 unit of X, Y decreases by 3, right? That's your slope over here, and it's negative, so it goes down by 3. Okay, so put in the context of the problem. If it's price versus price, that's what you would do. And let's see what else it would do. I think it was absences versus the grades. So for every 1 absence in a class, your grade will go up or down depending on what the problem is asking you. Okay, now we have what tools? We have the scatter plot and correlation coefficient to determine if a particular set of data can be modeled with a line. But the most reliable way to figure it out if a linear model is appropriate is actually hypothesis testing. Okay, what is your hypothesis testing going to look like? The null hypothesis will always say there is no linear relationship, basically saying that the linear model is not appropriate in this case. This is equivalent to saying beta 1 is equal to 0, basically saying the slope of the line is 0. So there is no line to model, right? If the slope of the line is 0, that means it's not a linear model. Okay? Alternative hypothesis will say, yes, there is a linear relationship between the 2 variables, okay? And it will say beta 1 is not equal to 0, or beta 1 is greater than 0, or beta 1 is less than 0, okay? If it says beta 1 is greater than 0, that means the linear relationship is positive. This means the linear relationship is negative. If it says something like that, that means, okay, we're not sure which one it is, but it's linear. Okay? Now, how do we do this? Well, thankfully, both TI-83 and 84 calculators have this command. So what would you do to do this? You would plug in your values into your table. And now, if this calculator ever turns on from the first attempt. Oh, come on. Okay, here we go. So let me see. All of the values are here. What are we going to do? Stat tests. And we're going to go linear regression t-test, right? Oops. That's not what I want to do. I don't want to do ANOVA. So linear regression t-test. Here we will go. L1, L2, let's see. What do I want to test? We want to test, in our case, it's positive, right? So in our case, we would say H naught, beta 1 is 0, HA, beta 1 is greater than 0, right? Because if you look at, let's go back to the scatter plot. If you look at the scatter plot, it's clearly positive. So that's what we want to test. So let's go ahead and test this. Okay, L1 here, L2 here, 1 for frequency, and I'm going to say greater than. Calculate. Let's calculate. Okay, let's take a look at this p-value. Ooh, I'm glad we got a p-value like this. So, you got your p-value. That looks like 2.296, so let me actually write it like this, 2.296 e to the negative 6, right? Now, this doesn't mean that p-value is 2. I want to make sure that you guys don't make that mistake again, because on previous tests, a whole bunch of people made that mistake. You said that, oh, okay, then it's 2.29. That's pretty large. That's greater than alpha level. We fail to reject. But this is really saying what? That p-value is 1, 2, 3, 4, 5, 2, 9, 6. That's what your p-value is. This is scientific notation saying put 6 zeros before the decimal. So 1, 2, well, 6 places before the decimal. So 5 zeros and 2, right? 1, 2, 3, 4, 5, 2, 9, 6. This is very, very small. Okay? That is less than alpha level, whichever one it is. It's going to be given to you. If it's not given, assume it's 0.05. But okay, this is very small. What does it mean? We reject the null. We reject H naught. What does it mean in the context of the problem? That means y hat is a good model. Is a good model to predict y from x. Okay, so this one basically says we're rejecting H naught. There is a linear relationship, right? So now combining all of the steps, let's see, scatter plot looks good, looks linear, R is really high, and then hypothesis testing, which is the most reliable way to figure it out if a linear model is appropriate. There is a linear relationship here, and there is a positive linear relationship. We can conclude that yes, this equation y hat is equal to what? What was it? 0.9 plus 1.77x is appropriate in predicting y. Okay, why is that? Well, the scatter plot looks good. It looks linear, and it looks very relatively strong. R is pretty high, and then the last thing that we just did, hypothesis testing, which is rejecting the null hypothesis, saying that there is no relationship. We just saw that there is, okay? And this p-value is very small, so there is a very strong evidence showing that there is a linear relationship. Okay, that's it. Thank you for watching.